So the first thing we're going to look at is an example that's basically review. We have an ambitious grade 9 student saving for their university education. At the end of every month, the student deposits $450 into a savings account at 3.5% interest. They do that for 4 years. And the question is, how much money would the student have saved? So that's 450. Okay, 4 years every month. It's 450 times 48 or 48 months in 4 years. So that's how much they would put away. And of course, it would collect interest. So we use our future value formula. Our payments are 450. Our interest rate is through 3.5% divided by 12 because it's monthly, and 4 years every month is 48 months, so N would be 48. So there's the calculation that will give you the final value, which is $23,148.94. Of course, we could also check our answer using our TVM calculator. Our present value in this example would be 0. The payments that the student makes were $450 per month. We're looking for the future value. The interest rate was 3.5%. And again, there were 48 months or 48 periods. And again, this one's already on monthly, so that's good. So I solve for the future value. And sure enough, I get the exact same answer of $23,148.94. So the goal of today's lesson is actually to explore a different type of annuity that has a different type of formula. And that, from the title of today's lesson, is the present value annuity or the present value formula. So I need you to really think about this scenario and kind of understand how different it is than the first situation. So you have a student who wants to have $500 every month for the first year of college, 8 months, to help pay for living expenses. So imagine this was you. Maybe you have already paid for your tuition, and maybe you are staying in residence or something, and you've also already paid for that. Of course, there are other living expenses associated with living on your own, food and entertainment and textbooks and school supplies and that sort of stuff. So let's say that that's $500 a month that you want to have now for those 8 months. Now, one thing to realize is that that's 8 times 500, okay, which is a total of $4,000. Sorry, $4,000. So you want $4,000 for your living expenses. Now, does that mean that so say you go to school in September, does that mean that you need to have $8,000 right away so that you can have $500 for every month you're there? Yes, I mean, that would work, but you don't actually need that much, because what you could do is you could put the money in a savings account and then make withdrawals. So as the money's sitting in your bank account, it's collecting interest, you're pulling the money out, but the money that's in there still collects interest. So I mean, one way of looking at it is you could take, in the beginning of September, you could put $4,000 in a savings account, and it would collect interest, and you have more than $500 a month. I mean, that's one thing you might do. But the other thing you might do is you might start with less than $4,000, pull out $500 every month, and then for your last month, you pull out the last $500. So we're basically saying what its starting balance must be in the account in order to have $500 a month. What do you need? It's going to be a little less than $4,000 because the money will collect interest. You don't need all that money right away. So this is a different type of annuity. So it's important to understand that in this annuity, okay, we have what's called a starting balance, or that actually is what's called a present value. Okay, so starting balance, the exact same thing as a present value. A person withdraws money as the balance collects interest. At the end of the annuity, the money is all gone. So in another way you could say is that the future value of this annuity is equal to 0 because the money would all be gone. So again, imagine putting some money into a bank account, a little less than $4,000, pulling $500 out every single month, and then your last year of school is the last $500. What is the amount that needs to go in there to give you that $500 every month? Well, that introduces the present value formula right here. So this is very similar to the future value formula. I mean, it's in the sense that it's a formula that's given to you. You don't really need to worry about where it came from. PV is the present value of the annuity. That's the starting amount that you'd start with in your bank account. R is payments, but in this case, they're payments that you withdraw, not put in. You're not saving in this case. I is the interest rate, and then N is the number of periods, or in this case, the number of times you take out money. So just to visualize this again, we're basically saying, look, in this kind of annuity, it's this situation where you have this lump sum at the beginning, a present value, and then there are regular payouts over time. So I've got 8 arrows here. You can imagine that each one of those represents $500 in this example above that you pull out. Okay, so that's a total of $4,000, okay, when you add all those up. So what's the present value? What's that amount that you would need here? That's what's called the PV value in the formula. Okay, so that's going to be a little less than $4,000. So you imagine taking a lump sum, dividing it up into equal payments that you'll receive, but adding up all the payments will be more than the present value because of the interest. So the next thing we're going to do is we're going to look at this example. How do we answer this question here using this PV or present value formula? So I've written the formula down here. Now we're going to sub in the values we have for this example. Okay, so there are payments, $500. These are payments we're receiving, or the student's receiving. Interest rate, 3%, but divided by 12 because it's monthly. And there are 8 periods or 8 months where we're collecting interest. Notice that's a negative exponent there. So we're going to put this in on our calculator. It's going to give us an answer. Now, just like with the future value formula, it can be a little bit complicated to get this amount into your calculator correctly. We also want to be really careful with rounding, that we're not, we're getting the answer to the nearest cent. Okay, we're not rounding in between calculations too much. Very important, the brackets here mean something as well. This number needs to be divided before the big division can happen. So I guess what I'll do now is I'll pull up my scientific calculator and I'll walk you through how I'm going to type this in on my calculator, and you can try the same thing on yours. Of course, pausing the video if you need to. Okay, so I've got my calculator up right now. Hopefully you can see that okay. I'm going to start by typing in the top of the fraction here. I'm going to go 500 times bracket. Now, some calculators you don't need to write the multiplication symbol right here between the 500 and the bracket. Some you do. I'm gonna include it just in case. Okay, 500 times bracket 1, subtract, open a new bracket, 1 plus 0.03 divided by 12, close the bracket. Okay, now I need a power of, and it's a negative exponent, -8 here. On this calculator, I hit my power button, and then I actually go -8. So on your calculator, you either do the same thing, or you have to type the 8 and then hit the negative sign. And then I'm going to close that last bracket. So there's the top of the fraction. Now, to break it up a bit, I can hit equals here on my calculator, just so that I can, just makes things a little simpler. So I know that that's equal to the top of the fraction. Okay, now I'm going to divide that by the bottom. And I do need to use the brackets here so that the division happens in the correct order. Bracket 0.03 divided by 12, close the bracket, hit equals, and there's our final answer, 3,955.37. That's the PV value. So it's important to understand that in this example, we've essentially calculated what the starting amount or the present value needs to be for this student so that they can have $500 in their account ready to withdraw every single month. So if we look at the picture again, we basically found out that this magic number here is 3,955.37. Okay, that when you take 3,955.37, you can break it up into 8 $500 spread out over 8 months. Okay, which gives you a total of 4,000. So you can see the interest isn't that much. The interest is just $4,000 subtract 3,955.37, so about $45 in interest. Okay, we've been talking a little bit about RRSPs and retirement and that kind of thing as a method or something you might save for. So we've been using the future value formula so far to figure out if I save, say, $100 a week or $500 a month or whatever it might be, how much money will I have when I go to retire? Now we look at the other half. Suppose I think about how much money I need to have for my retirement. So what happens when you would, retire and want to live off of your savings is you would have some big, large sum of money, okay? And what would happen is that sum of money would immediately collect interest. So say day one of retirement, okay, hopefully I'm on a nice beach somewhere, and I have this big bank account full of money. And what happens is every month or every week or whatever you might decide, you're going to make withdrawals from that sum of money. So think of smaller withdrawals, however much decide you need to live off of. So in this example, decided that those small withdrawals should be $3,500 a month. So I've decided that when I retire, I'm going to live off of $3,500 a month. That large sum of money that I'm getting the $3,500 from, that's still collecting interest. So your money when you retire, or when you think about retirement savings, the money collects interest while you're saving for your retirement, but then while you're retired, it continues to save money. So imagine I retire with $500,000. I don't need that $500,000 on day one. Okay, that's not a smart way to spend your money. So that money collects interest while I'm taking it out. Okay, and it collects a lot of interest. So in this case, retirement income plan, which is basically a plan that allows you to withdraw money as your money collects interest. Okay, so that pays 6% interest, let's say, compounded monthly. And suppose I plan on being retired for 30 years, or at least I want to have enough money for 30 years. How much must I have saved by the time I retire? So that's like the present value. So what's the starting amount that needs to be in my retirement bank account? If you want to think of it that way, that's this big lump sum. What's that starting amount need to be so that I can take $3,500 out for 30 years? So again, it's the same type of annuity as in the college example. You're starting with a large present value and you're breaking it up into payments that you're going to take out. So here our R value is 3,500, the payments. Interest rate, of course, is 6% divided by 12. And the 360 is our N. And I get that from saying 30 times 12, 30 years, 12 months in a year. So I'll need 360 payments of $3,500. So if you look at these arrows and imagine this is you slowly withdrawing from your big bank account, there's 360 of them, and they're all $3,500. Okay. If you took $3,500 and multiplied it by 360, that would be all the money I collect when I retire. Okay, it's a big number. Okay, it represents $3,500 a month for 30 years. 360 times 3,500. You'd find that that number, though, is larger than the number you actually need to put away because, of course, your money collects interest. Use a calculator similar to the last example, get that in, and you should get this answer right here, 583,770.65. Let's just think it's really important in these examples to actually understand what it is you've just calculated. Mr. Elliott would need to have his savings worth this amount, $583,000, in order to withdraw $3,500 per month for 30 years. So that's the magic number that gives me this. Now, there's a lot of interest earned during these 30 years. So you need to think about being me for a second, okay? Collecting this $3,500 per month for 30 years. That's the money you collect, 3,500 times 360. That's how much you get. And if you were to calculate that, I'll just do that right now, make sure I get it right. Okay, you get about $1.26 million that you end up collecting, which means that your $583,770.65 you put away collected this much interest, $676,000 of interest. So there's a lot of interest in this example. And that's just the second half of retirement. You collect a lot of interest while you're saving for this amount right here. And then you collect interest while you're withdrawing from this amount right here. Okay, so it's like a doubling thing. You get twice as much money on $500,000 from the interest. Why? Well, $500,000 is a lot of money. 6% is a pretty big interest rate compared to some of the other examples we've looked at. And the big thing is time. Okay, you have 30 years while some of the money is collecting interest. Now, the amount of money collecting interest is constantly going down, okay, because you're constantly pulling out that $3,500, but still, you put away this amount, okay, this money collects interest for the first month, then you take $3,500 out. There's still a lot of money in here, Okay, you take another $3,500 out the next month. Well, there's still a lot of money left collecting interest. So it slowly decreases over the 30 years. Okay, in this next example, we have this person, Joe, who retires with $450,000. And let's assume that all the other amounts, so they're going to put, just Joe, sorry, is going to put this money into an annuity and receive regular payments. So the $450,000 is like the big amount of money that he has saved. And through his retirement, he'll make withdrawals from that. And we're going to assume that all the numbers are exactly the same as in this example, that he's going to have 30 years of retirement. He's going to collect interest at 6% again. But the big difference here is instead of having an R value, we have the PV value. So in the other example with Mr. Elliott, we had the R value and we figured out what present value or what starting amount he's got to retire with in order to get $3,500 a month. So in this case, we had these, but we didn't have the big number amount. So now it's the other way around. So it's like we have this formula and we know what the PV is. Okay, it's that 4,500, and we don't know what the R is or the payment amount. Well, just like we did with the future value formula, we can rearrange this formula to solve for R. If we multiply both sides by I and then divide by the square brackets, the exact same way we did with the future value formula, we'll get this formula right here, which is the exact same formula but rearranged for R. So really in our original formula we came up with, we could also have said that the formula could also be rearranged to solve for R like this. Once we get that far, it's just a matter of plugging in the correct values for PV, for I, and for N, okay, using the same examples as before. Okay, Joe has 450,000, so that's his present value. This is his interest rate. Okay, 6% divided by 12 for months, still 30 years or 360 months. We type this into our calculators and come up with a final amount of $2,697.98. So less than $3,500, which should make sense, because in the other example, it took like $583,000 to get $3,500 a month. So if you only have $450,000 a month, you're obviously going to get a monthly payment of less than $3,500. And just to summarize, Joe could invest his $450,000 and collect $2,697.98 per month for 30 years. That means that there's so the idea here is the big money, the big amount that you start your retirement with is $450,000, and then the amount that you get over 30 years, okay, if we imagine these as like deposits, would be the $2,697.98. So really, Joe collects this money right here in brackets. He gets $2,697.98 360 times, and that only costs him $450,000. So he's going to get more money than he put in because of the interest. So the difference is the interest. Again, another massive number for interest, $521,000 in interest. 30 years over 6%, you're going to find that there is a lot of interest. The last question on today's lesson is kind of one of my favorites. Suppose that you were lucky enough to win the jackpot in the lottery, and I'm going to say that you won $5 million. Now, if you were smart with your money, what you could do is you could take that $5 million, the big amount of money, and you could put it into an annuity that collects interest. Now, I've said the interest is 4%. In reality, if you had $5 million, you could probably come up with a better interest rate than that, because when you have money, you tend to be able to get good returns on the money, but we won't worry about that right now. So you got this $5 million. If you were smart, you would put it into an annuity and make regular withdrawals from it and then live off of that money. Now, what could happen is suppose you decide you're going to get weekly payments on the money, and you're going to do that so you're young, so let's say for 75 years. So that means that every week, you're going to withdraw a bit of money from the $5 million as the money's collecting interest. Now, if you wanted to plan that out, you could figure out what's the most I can take out every week, so that at the end of 75 years, there would be no money left. Well, we might try to figure out like how many withdrawals would that be? Well, 75 years is equal to 52 weeks in a year. We're going to assume exactly 52 weeks in a year. That's 3,900. So that's actually your end value. The number of withdrawals is 3,900 withdrawals if you take it out. So we can use, again, this formula to figure out what is the most each withdrawal could be. Okay, what is the amount that you withdraw 3,900 times that would use all the $5 million up? So our present value is $5 million. Our interest rate is 4% divided by 52 because it's a weekly interest rate we want. And then on the bottom of the fraction, okay, we have 1, we have our I value again, and then we have our N value, 3,900. If you figure that all out, you should get $4,407.92. So that's every week you could withdraw $4,000 a week because you have $5 million. That's an incredible amount of money. Okay, you can definitely live off of that quite happily. Now, one thing we might decide to calculate here, I mean, that's the end of this question, but let's just look at some of the numbers. You're actually getting 4,047.92 3,900 times. If you figure that out, I'm just going to do a rough estimate there. I'm not going to bother with exactly. I mean, it's like almost 16 million. It's very close to $15.8 million. So your $5 million over 75 years, even with you taking money out, still means you ended up collecting a total of about almost 16 million. Your money triples because of the interest. You're very rich. The other thing you could do is, interestingly enough, if you look at the top calculation here, where we took $5 million and we were to take that $5 million and in that calculation, 2, 3, 4, 6, we multiply by the monthly interest rate, just like that. So that actually gives you, like, imagine that you collect the $5 million, you put it into the annuity, and you wait 1 week and you don't do anything. Well, during that week, there's your weekly interest rate, 4% divided by 52 times 5 million. That's just the interest that the money would collect while you didn't do anything with it for a week. That's actually a fairly large number. It gives you, just 1 second here, about $3,800, $3,846. If I just round to the nearest dollar. So that's how much interest $5 million collects in just 1 week. Now, in this example, you've decided to take out $4,000 instead because you are dipping into the $5 million. You're going to take that money out for 3,900 times, so eventually the $5 million's gone. Another thing you could do if you're smart is you could just live off the interest for now, like $3,800 a week. You could do that forever without ever touching the $5 million. Just keep it in the bank account, collect the interest. That'd be a really smart thing to do, I think. Okay, that's it for this lesson. Thanks for tuning in.